First of all, a rational function is defined as f of x equals p of x over q of x, where p of x and q of x are polynomials and q of x is not 0. Simple way of putting that, it's a fraction where you have x's in the denominator, possibly the numerator too, but definitely in the denominator. Here's an example. The simplest rational function is 1 over x. 1 over x is also known as the reciprocal function. Here we have a graph of it, and note from the graph that as the x values move away from 0 to the right, as x goes towards infinity, the y values approach 0. The same is true as the x values go away from 0 to the left. As x gets further and further into the negatives, y gets closer and closer to 0. As the y values move away from 0 in the positive direction, in other words, as you look upward on the graph, you see that the x values approach 0. And as the y values move away from 0 in the negative direction, you see that the x values approach 0 there as well. Because of this, x is considered a horizontal asymptote, and y is a vertical asymptote of the function 1 over x. What this means is that these are lines that the graphs will not cross. Now we're going to alter that definition just a little bit as we go on, but for now think of them as lines that the graphs will approach but not cross. This is a summary of the reciprocal function. The domain is negative infinity to 0 and 0 to infinity. X cannot be 0 because you cannot have a 0 denominator. The range is the same because since x cannot be 0, y is never going to be able to be 0. You see it graphed by hand on a calculator, and then you see the table. Notice that where x equals 0, y1 says error. You cannot have a value there. This also reminds us that the function is decreasing from negative infinity to 0, and it's increasing as x goes from 0 to infinity. It is discontinuous at x equals 0. There's a discontinuity there. The y-axis is the vertical asymptote, and the x-axis is the horizontal asymptote. It is an odd function. If you flipped it upside down, it would look completely the same. And that means that the graph is symmetric with respect to the origin. This graph can be shifted, translated, and reflected to get different, more interesting graphs. For example, the graph of y equals negative 2 over x. Okay, let's look at how this is going to, what this is going to look like. The expression could be written as negative 2 times 1 over x, and going back to what we learned about our transformations, what that means is that we're going to be stretching 1 over x vertically by a factor of 2, and we're going to be reflecting it across the y-axis. Or you could say across the x-axis. In this case, it doesn't matter. It means the same thing. It results in the same thing. So there's what the graph is going to look like. Now, you try this one. Give the recording a pause, give it a try, and resume the recording to check your answer. Okay, the 2 can come out front, so you have 2 times 1 over x plus 1, and the 1 underneath tells us that the graph is going to be shifted 1 to the left. It's also going to be stretched vertically by a factor of 2. Now, because the graph has been shifted to the left, that's going to shift the domain. The domain is also going to shift to the left, so instead of negative infinity to 0, it's now going to be negative infinity to negative 1 and negative 1 to positive infinity. The vertical asymptote then will be x equals negative 1. We didn't shift it in the y direction, so the horizontal asymptote stays the same. Now we're going to use division and translations to graph this and give the domain and range. What we mean by that is you're going to use synthetic division to write this as a quotient plus a remainder, and then you're going to use that to do the translations, give the domain and range. Why don't you pause this, give it a try, and resume the recording to check your answer. Okay, so we're rewriting it. We divide x plus 1 into x plus 2, and we get 1. With a remainder of 1. So we have 1 plus 1 over x plus 1. What that means, if you're thinking about your transformations, is that we are shifting this graph of 1 over x to the left 1, and it's also going to shift up 1. Here we go. Notice that our new asymptotes, instead of 0 and 0, 0 for the x, 0 for the y, our new asymptotes have become -1. X equals -1 is our vertical, and y equals 1 is our horizontal. So everything moved up 1 and left 1. The domain and range have also moved up 1 and left 1. The domain is -infinity to -1 now, and -1 to infinity. And the range is -infinity to +1 and +1 to infinity. Now, this is just another reminder that if you have an older calculator, they tend to put lines in there that should not be where there are discontinuities. So a non-decimal window or connected mode connects plotted points. A decimal window or dot mode plots them without connecting the dots. Older calculators will connect parts of the graph that should not be connected, and using a decimal window or dot mode will correct this if it bothers you. Newer calculators don't have this problem, and the graphs will look fine, and you shouldn't need to worry about that. Now we're going to look at the function 1 over x squared. Notice it looks a little different. This time everything is above the x-axis. The domain is still -infinity to 0 and 0 to infinity, but this time the range is just 0 to infinity. Here you see it graphed by hand on a calculator, and then you see the table. It's increasing from -infinity to 0 and decreasing from 0 to infinity. It is discontinuous at x equals 0. The y-axis is a vertical asymptote and the x-axis is a horizontal asymptote. This function is even, which means it's reflected across the y-axis. So now we're going to graph this, and again, use what you know about transformations. Pause the recording, give it a try, and resume the recording to check your answer. So what's happened here is that the graph has been moved left 2 and down 1. And so everything shifts, including the domain, the range, and the asymptotes. You can see what we have there. All right, the rest of this is just some practice. So pause the recording, give it a try, and resume the recording along the way to check your answers.